Thank you, Susanna. Our final speaker today is Loren Frank. Loren's lab uses a combination of techniques, including multi-electrode recording, real-time feedback, behavioral manipulations, and optogenetic circuit manipulation to study the neural bases of learning, memory, and decision-making. His long-term goal is to understand these processes well enough to develop approaches to treating memory-related problems, such as learning disabilities and Alzheimer's disease. Loren has received numerous awards, including the Society for Neuroscience Young Investigator Award, and just last week, he was named a Howard Hughes Medical Institute investigator. The title of his talk today is The Neural Substrates of Memory. Loren.
Thank you. Thank you. And it's a great pleasure to be here today. It's a particular pleasure to follow the beautiful talk because Susanna's work so beautifully illustrated why memory is important. But I can't resist, nonetheless, showing you this clip from the movie Ratatouille, for those of you who haven't seen it. This is towards the end of the film. This is the food critic here tasting the restaurant's ratatouille. And, oops, sorry. He does so. Oh, come on, you can do it. There we go. He does so he has this sensory experience aided by saliva, critical component of this. He tastes it, and it drives this remarkable mental time travel back to his past, where he remembers coming in from outdoors into his house. He remembers his mother. He remembers her taking care of him. This entire episode comes back to him, and perhaps most remarkably to me, it does so in a flash. And I think this really beautifully captures why memories are important, the impact they can have on our lives, just as Susanna explained to us. And this is what we're trying to understand in my laboratory. How does the brain do this? All of us have this remarkable ability to store the memories for the events of our daily lives. As Susanna beautifully pointed out, that's what you used to get here today. None of you would be here if it weren't for your memories. Right? The whole point of being here is to relive things and to create new memories. And we'd like to know, how does that work? How does the brain make this possible? And so what I'm going to tell you a little bit about is what we've learned about how the brain does this, and specifically what's happening in the brain when a memory is retrieved. Now, in my laboratory, we also use a model system. We use rats in our laboratory, and we study how their brains change as they learn, remember, and then use those memories to guide their decisions. And so the first question we like to ask is, well, what is a memory? What parts of the brain are involved? How are they engaged in this process? And so, well, where do we begin? Well, clearly, a memory begins when things from the outside world impinge upon our senses. Our eyes, our ears, our nose, all of this brings in information to us. That information is sent through many areas and is processed in parts of our brain called the cortex, the visual cortex, which specializes in things that we see, the auditory cortex in things that we hear, olfactory in things that we smell, and so on and so forth. Now, these are all areas that are specialized for extracting information from the world, for understanding what we're seeing and hearing and smelling. And all of these areas can change when new experiences come in, but it turns out that change, that plasticity, that ability to adapt is actually quite slow in these areas. Now, that's actually a good thing. You don't want to look at an apple one day and have your brain completely rewire so that the next day it looks totally different. Right? It's really important that we have stability in our ability to perceive the world so we know the same thing day after day. But that's a problem if you want to store memories for the events of daily life, because those events happen exactly once. All right? Now, fortunately for us, evolution worked out this neat trick of passing this information to a brain structure called the hippocampus. It's called the hippocampus because it looks a bit like a seahorse. And the old anatomists named things by what they looked like because they had no idea what they did. And this area is down here in the temporal lobe, sort of near your temples. And it is a site of unbelievably rapid plasticity. That is, the connections between the nerve cells, their properties, they can change extremely quickly. And the idea here is that what the hippocampus does is basically take an ongoing snapshot of all of the experiences of daily life. And it does so in such a way that afterwards, say after this, if you go back to UCSF, you can then retrieve that memory. And here the idea is that the hippocampus is acting something like an orchestra conductor. What it's basically doing is saying, for example, hey, if you want to remember that scene from your childhood, you neurons in visual cortex associated with what your house looked like, you guys turn on. You neurons in limbic areas associated with emotion, you guys turn on. And the hippocampus creates this pattern of activity across the brain that reinstates the memory. But there's something else really important about this retrieval process that we often don't think about. Right? I can ask you to say, think back to the breakfast this morning and the discussion of why UCSF is an amazing place and the stories of Cambridge and so on and so forth that you heard. And if you were to imagine telling somebody about what you heard this morning, you might say, well, there was this discussion of what made UCSF special, and you might talk about that for a couple of minutes. But none of you would spend an hour and a half saying things like, well, I sat down at the table, and then I took a fork, and I put it into my eggs, and I brought it to my mouth, and I chewed, and then I heard the following words, right? Or if you do say that, you are way too boring and need to stop. That's really important. Our memories are absolutely not moment-by-moment recapitulations of experience. What they are massively time-compressed snippets that we can bring back up, right? That's really important. You don't want to ask, say, a patient you're working with, so tell me about your childhood, and emerge from the conversation 12 years later, right? Not helpful. You'd both be dead by then. So it's really important that our memories be time compressed, that they be able to take stuff that happened to us, bring it back up quickly, and that's important because our memories guide our decisions. They guided us all to be here today, for example. And so what we're looking for then in the brain, for a pattern of brain activity that might be a memory, is something that happens but much faster than real life. And I'm going to tell you about what we think that is. We think we've discovered that pattern and are trying to understand how it works, how it's created, and how it's used. Now, to tell you about that, I need to tell you a little bit more about what happens in the brains of rats and similarly the mice that Susanna talked about when they wander around, for example, a place like the maze she showed. So it turns out that if you put electrodes in the hippocampus, and this is true for people too, epileptic patients where they measure these things, and you have the animal walking around, you'll have individual neurons, brain cells, in the hippocampus that are what are called place cells. So individual cells are active, and that means they fire off these things called spikes, and we can actually listen to them. So one neuron might go bump, 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 and then its neighbor in the next place might go bump, 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 and so on and so forth. So if you imagine some experience, like the mouse finding the Palace Hotel in Susanna's task, you would see a bunch of neurons, bump, 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 and so on. So what would it look like if later, if the animal were remembering that event? Well, we know it's faster than real life, so we might expect ba-bup, 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 all the way through. And it turns out that's exactly what happens in the brain all the time. So what we find are these amazing events we call memory replay events, where we see the same sequences of brain activity that we saw during behavior, but they're sped up by about a factor of 20. So an experience that might have taken 30 seconds or so now takes 100 milliseconds, a tenth of a second. All right? Now, this looks like a memory. It looks for all the world like the brain is creating this pattern and playing out this snippet. The real question is, can we make a causal statement about that? Can we actually link that particular pattern of brain activity to the ability to retrieve something and use it to guide decisions? And so what we did is we built a system that allowed us to detect when those events were happening, and then in real time, we could turn off the hippocampus for just a tenth of a second. And then it came back online and did its normal thing. And this allowed us to selectively turn off those events where the animal brain was replaying things while leaving all the other activity of when those cells were active while the animal's wandering around intact. And that was enough to severely impair the animal's ability to make memory-guided decisions. All right? So we're starting to learn what these events look like, what a memory is. And I just want to end with sort of the point that, why should we do this, right? This is very basic science. We're working in rats or mice. In our case, we're really just trying to understand what's going on. And I guess my point is, all of you know we are very, very impotent in many ways at treating things like brain diseases. Thanks to work like Susanna's, we're getting better, but we have a hugely long way to go. And part of the reason for that is we simply don't understand how this thing works. And it's really hard to fix something if you don't know how it works. So from my perspective, it's really important that we're doing research that spans the spectrum, from very basic, what's going on, to applied, how do we prevent immune cells from invading the brain? And I think that's one of the things that I'm so grateful to UCSF for, is providing the environment where all of us can work together towards those common goals. Thank you.